Welcome to Lesson 2 of Module 2 on processing text. In this lesson, we will discuss text preprocessing and vectorization. How can you use text data in ML? ML works with well-defined numerical data and cannot understand text. The process involves taking text data, preprocessing it, vectorizing it, and then finally using it to train your ML model. This lesson will explore the text preprocessing and vectorization steps. Let's start with text preprocessing. Text preprocessing involves cleaning the raw text data before feature engineering. Let's review how to clean text data. Remember that it is difficult to find patterns in unorganized text, and preprocessed tasks are needed to normalize the text by removing noise. Several ML libraries offer tools for this cleaning task. The slide presents a nice example of cleaning text. However, keep in mind that cleaning text data is truly task-specific. For example, in sentiment analysis tasks, some words might be kept in capital letters because they can represent an emotional state present in the text. Recall that tokenization is the process of breaking text apart by white space and punctuation. It helps interpret meaning by analyzing the sequence of words and separates words or sentences. For example, the sentence, "I don't like eggs," would be tokenized into smaller components. The resulting tokens are then used in the next steps of text preprocessing. After tokenization, you have tokens. The stop words removal process has a list of stop words, which are frequent words that don't contribute much to the overall meaning of the text. You compare your tokens with the stop word list and remove the tokens that are on it. For example, "There is a tree near the house" would become "tree near house" as the stop words of there, is, a, the are removed. The Natural Language Toolkit, NLTK, is a popular Python library to work with and model text. The toolkit has tools to load and clean text. NLTK also provides an extensive list of common stop words for a variety of languages. The image on the slide shows the common stop words for English. Add stop words as needed or decide to allow some of these words in your text. The decision depends on your particular task. For example, against might be a meaningful word to have in a binary classification task for product reviews, positive or negative review. Let's review stemming. To further reduce the vocabulary and focus on the general meaning of the words, rather than deeper meaning, you can reduce words further by removing affixes, in particular, suffixes. For example, the words playing, played, and plays all reduce to play through the process of stemming. Note that stemming doesn't usually work with irregular forms, such as the irregular verbs taught and brought in English. You can use your own text dataset to experiment with stemming rules and other lexicon-based cleaning options, such as lemmatization. Note that the texts that have been shown so far are small and would be cleaned or processed quickly. Real text data is frequently long and messy. Text preprocessing might take a while to complete. Lemmatization is an important aspect of natural language understanding, NLU, and natural language processing, NLP. Similar to stemming, lemmatization reduces inflection forms and sometimes derivationally related forms of a word to a common base word. Stemming relies on a simple heuristic process to remove derivational affixes, but lemmatization transforms text by using a vocabulary and morphological analysis of the words. The objective is to obtain the base or dictionary form of a word, which is known as the lemma. A lemmatizer performs full morphological analysis to accurately identify the lemma for each word. Doing a full morphological analysis produces modest benefits for retrieval. This slide compares stemming and lemmatization. Both techniques convert words into their base forms, but they do so in different ways. Stemming is a rule-based method that creates substrings that correspond to a simpler form of a given token. The process removes the extras from the start or end of the token. Lemmatization is more involved. It uses a grammatical approach, so it can handle more difficult cases, such as irregular forms. The goal of both methods is to produce simpler or more general meaning tokens. Let's continue with vectorization. Vectorization involves transforming text features into numerical format. Let's review the bag of words method to vectorize text. The bag of words method is a special technique to convert text data into numerical form. This method is usually considered less modern, but it's still useful to learn. This method represents the text as a bag of words and disregards the grammar and order of words. The steps are as follows. 1. Construct or borrow a vocabulary of words. If you don't borrow a vocabulary, you can create one by using the training data. 2. Create simple numerical vectors by calculating the occurrences of words in your text data. The vectors can be binary, whether the word occurs, simple word counts, or frequencies, which are normalized according to the total number of words in the text. Consider the example on this slide, which uses the following sentences. It is a dog. My cat is old. It is not a dog, it is a wolf. The binary bag of words method first looks at the text and creates a vocabulary of the words that were encountered across the text. The vocabulary for these example sentences is listed alphabetically in the top row of the table on the slide. A, cat, dog, is, it, my, not, old, wolf. This is a fixed-length vocabulary of 9 words. According to the position of words in this vocabulary, the binary method assigns to each sentence a 9-dimensional vector that is filled in with ones and zeros, similar to one-hot encoding. The ones and zeros indicate whether the respective word appears in the sentence. The scikit-learn library offers easy-to-use tools to perform both tokenization and vectorization of text data. The slide shows example code for the count vectorizer. The code takes the following 3 sentences. This is the first document. This is the second document. And the third one. From these 3 sentences, count vectorizer creates a 9-word vocabulary and then applies the transform function on the sentences. The sentences are vectorized, and the resulting array is displayed on the slide. Note the binary equals true parameter in the call to count vectorizer in this example code. If binary equals false were used, the vectorizer would produce word counts. In this case, the resulting array would probably be the same because none of the sentences have repeating words. If you don't want raw count numbers, you can normalize them. Term frequency does that. Normalizing input data for ML models has advantages for certain models. To calculate term frequency, you take the number of occurrences for a term and divide it by the total number of words, or tokens, in the text or document. The term frequency value is larger for words that appear more frequently in the text. You can pass the term frequency values into your numerical representation in a normalized way. Now that you have seen how to convert text data into numerical data, one thing not yet discussed is the vocabulary words themselves. How frequently do you see the word dog or plane or kid across all documents? Why does this even matter? Sometimes, in text data, rare words can be decisive about the overall meaning of a text. For example, imagine that you want to differentiate between documents about sports. You have documents about baseball, basketball, and soccer. Some words are common across all the documents, for example, supporter, field, player, team, ball, sport, jersey. Those words won't be helpful to identify a specific sport. Some words aren't common and can be useful to differentiate between the sports. For example, goalie for soccer, pitcher for baseball, and point guard for basketball. Another example is Galaxy for soccer, Dodgers for baseball, and Lakers for basketball. With these words, you can almost automatically know which sport a document refers to. Inverse document frequency, IDF, assigns a weight to each word, depending on how frequent that word is across all documents. The weight is large if the word is rare and small if the word is common. This method incorporates the idea of word importance into the bag of words method. How do you use inverse document frequency, IDF, with term frequency? You can multiply the frequency of each word by the weight of the word. This is called TF-IDF. The result increases the values of the rare words while reducing the values of the words that are more common. This can help ML models to identify important words in text data. You can use the scikit-learn library to perform TF vectorization as well as IDF vectorization with the same module. What if you want to capture some word forms? You shouldn't break them because meaning could be lost. For example, ice cream and New York. N-gram is a technique to increase the span of words that are considered. For example, with 2 gram, 2 consecutive words are considered as a single word, and the scores are calculated accordingly. Note that if you apply this on regular single tokens, you might explode the number of features. Always check the shape of your bag of words features in your code. In the next lesson, you will learn about word embeddings and how they are obtained. Thank you for watching.